So, what exactly is a square root anyway? I mean, other than a bunch of letters and numbers with a crooked line covering them, that is. Well, to understand the square root, we need to understand its inverse, or opposite, which is squaring. For example, we can square the number 4. We know that this means multiplying 4 by itself, or 4 times 4. But you can also think about each of these 4's as being the lengths of two sides of a square. If we make a square that is 4 units on each side, its area is 16 units. 16 then is the result we get from squaring 4. So what about the square root? Well, we have to undo the squaring that made 16 to get back to 4. So, imagine that this square has actual roots. This root of the square, the bottom row, which is 4, is the square root of 16, the area of the whole square. So, where are square roots found? Well, any place where numbers are squared. For example, the D'Addario Company manufactures guitar strings. They publish information about their strings in order for musicians and instrument makers to be able to design and use guitars. A guitar string creates a lot of tension force on the neck of the guitar, so it's important to choose the right string to keep tension in a safe range. To calculate string tension, we have to know a thing or two about the string and how it will be used. These things are called variables, and depending on their values, different tension forces will result. UW is called the unit weight of the string. It's how many pounds 1 inch of string weighs, so we would expect this to be a pretty small number. The scale length is the vibrating length of the string. For a typical guitar, this is about 25 inches. Pitch is the note that the string will sound when it's properly tuned. And finally, the formula for string tension is given here. It's dependent upon the independent variables we just learned about. Suppose I have a PB053 D'Addario string just laying around here, and I want to see if I can use it on my guitar. So at the top of the screen is the formula for the tension that's given from the D'Addario catalog. Okay, I'm going to rewrite it so that we can solve it for the pitch F. Now I know that the guitar can hold up to 180 pounds tension on the neck, and with 6 strings, that means that I can put about 30 pounds of tension on each string. The vibrating length of the string is 25 inches, and I'll go ahead and get the unit weight from the D'Addario catalog. So here's the PB053 that I have. It's listed here. I'm going to go ahead and fill in the unit weight from the catalog. So let's go ahead and solve this now. First thing to do is to fill in the formula with whatever information we have. We want to solve this for the pitch F. Now notice that F is inside the parentheses with some other numbers, and the whole thing is squared. And if I square a whole bunch of numbers that are multiplied together, I have to square each one of them separately. So I can rewrite it like this. Now I'm just going to run all these numbers through the calculator and simplify, and I get this result. And then finally, to get F squared, I'm going to divide both sides by 0.003685, and that's going to give me F squared is about 8140. Now to get F, I'm going to have to take the square root of both sides, because the square root is the inverse of squaring. So if I take the square root of F squared, that's going to leave me with just F. And I see that F is going to be about 90 hertz for the pitch. And that means that I can tune this string up to about 90 hertz, which would give me about 30 pounds of tension on that string. So I can use this for the lowest E string on the guitar, which is normally tuned to 82.4 hertz, but I would have to be pretty careful not to overtune it. Before we look at square root specifically, let's look at inverses of functions in general. The inverse of a function allows us to undo it. We can undo subtraction with addition, or undo addition with subtraction. Multiplication and division are inverses. Logarithms and exponents are inverses of each other. And squares and square roots are inverses of each other. Inverses are the key to solving equations. We apply all those inverses listed above in order to solve equations. A function gives us a y value when we give it x, and its inverse will give us back x if we put that same y value back into it. So here you see a function, x plus 6, that has an input of 3. Its output is 9. If we take that y value, 9, and put it into the function's inverse, x minus 6, the output becomes 3, which is what we started with, the original x. So let's look at how we can find the function's inverse. If we have a table, all we have to do is switch the values in the x and the y columns. If you have a graph, simply reflect the graph over the diagonal line y equals x. This is really the same thing as replacing each point on the graph xy with yx, again switching x and y. If you have an equation, switch x and y and then solve for y. The inverse of a function f of x is written in the notation that you see on the screen. So let's look at finding the inverse from a table. All we have to do is switch the x and y values, so the table at the top in blue becomes the table at the bottom in red. From a graph, we're just going to switch x and y by reflecting the graph over the diagonal line y equals x. So if we start with this graph, we have our diagonal line y equals x. You can see that the red graph is the reflection of the blue graph. And notice that each point is reflected across that line, and the y value becomes the x value, and the x value becomes the y value. You also want to be sure that you recognize that when you find the inverse of a function, you're also switching the domain and range because we're switching x and y. So the domain of the function becomes the range of the inverse, and the range of the function becomes the domain of the inverse. If we have an expression, an equation, we can find the inverse first by switching x and y, and then we solve for y. For example, if we have y equals 2x plus 3, we'll switch x and y and get x equals 2y plus 3. Now we just need to solve for y. Subtract 3 from both sides, divide by 2, and we have the inverse y equals x minus 3 divided by 2. Trying this with the squares and square roots, here's a problem, y equals x squared plus 3. We'll switch x and y so we get x equals y squared plus 3. Subtract 3 from both sides, and then find the square root of both sides to get y equals the square root of x minus 3. So let's see how we can use squares to undo square roots and solve square root problems, and to use square roots to undo squares and solve squared problems. We know that squares and square roots undo each other because they're inverses. So here's an example. 2x squared plus 2 equals 10. What we want to do first is to isolate the squared variable x squared. So we'll get rid of the plus 2 first by subtracting 2 from both sides. And then we'll get rid of the 2 in front of the x squared by dividing both sides by 2. Now we have x squared isolated, so we'll take the square root, and we see that x equals plus or minus 2. The reason we have plus or minus is because both plus 2 and minus 2 equal 4 when squared. Whenever you take the square root of a number, you're going to get a plus answer and a minus answer. Here we have a square root problem. Once again, we want to isolate the radical first. We want the square root of x plus 3 by itself. So we'll divide both sides, in this case, by 5. And then we'll go ahead and square both sides. And we see that we have x plus 3 equals 9. To get x by itself and solve for x, we'll simply subtract 3 from both sides, and we see that x equals 6. Let's take a look at the graph of the square root. We see that the domain covers all x values starting at 0 and going to positive infinity. So the domain is only the set of non-negative numbers x such that x is greater than or equal to 0. We have a similar situation for the range. The range goes from 0 on up to positive infinity. So the range, again, is only non-negative numbers, y such that y is greater than or equal to 0. Transformations of the square root function are just like transformations for all the other functions that we've studied. The parent function is square root of x. And so we can apply various transformations to give us the transformed function. We have a negative sign in front flipping the graph or reflecting it over the x-axis. If there is no sign or we have a positive sign, there's no change. The value of a stretches the graph if a is greater than 1 or compresses it if a is between 0 and 1 in the vertical direction. The value of h, this is inside the radical next to x, the value of h is going to shift the graph horizontally by h units. Remember, this is backwards, so x plus h is going to the left, x minus h is going to the right. And finally, the value of k outside of the radical will shift the graph vertically up or down by k units. Adding k shifts up, subtracting k shifts down. So here we have an example of a transformed square root function. We see that it's reflected, so we know that the sign is negative. It has a vertical stretch by a factor of 2. It's shifted left from the origin by 1 unit. That means h is negative 1. And it's shifted down from the origin by 4 units, so k is negative 4. That results in the transformed function that you see on the screen. Remember, since h is negative 1 and we're subtracting h, we get x plus 1 inside the radical. The domain of this transformed function is now going to be all values of x greater than negative 1, since this graph has been shifted to the left by 1. And a similar situation with the range. Since it's reflected, we're going to look at all values below the start of the curve, which is at y equals negative 4. Sometimes it's easier to solve an equation or an inequality using a graph instead of algebra. So here we have a graph of two functions, and we have them set equal to each other for an equation. So we have negative 2 times the square root of x plus 1 minus 4 is equal to negative 8. For an equation, solving it is just as simple as finding the intersection. Use the calculator's intersection function to find the point 3, negative 8. So the solution is just the x value, x equals 3. If you plug in x equals 3 into the original equation, you'll see that it's true. Now suppose that we have the same two graphs, except now we want the square root function to be greater than negative 8. What values of x make that true? Well, if you look at the graph, what we're really looking for is where red is greater than blue. Where is the red graph greater than the blue graph? And this occurs from x equals negative 1 all the way up to 3. Now we have to be careful about this because the reason that we only go to negative 1 is because the domain of the square root function, this transformed square root function, only goes to negative 1 because it's the parent function shifted left. In addition, we're looking for where is red greater than blue. We know that at x equals 3 they're equal, but we don't want them to be equal. So we're going to go right up to 3 but not equal to 3. So we can be equal to negative 1, all the values between negative 1 and right up to 3 but not including. So the domain starting at negative 1, the graphs cross at x equals 3, and the solution is as written here. Negative 1 is less than or equal to x is less than 3. To summarize what we've talked about today, our parent function is f of x equals the square root of x. We know that the square root is the inverse of the squared function, x squared. And what we mean by inverse is that inverses undo a function. Finding an inverse means switching x and y. If we have a table, we just switch the x and y columns. If we have a graph, we're going to reflect over y equals x. This is the same as replacing each x-y pair on the graph with y-x. If we have an expression, an equation, we're going to just switch x and y and then solve for y. To solve square root equations, what we want to do is isolate the radical, and then we're going to square the square root. And to solve an x squared, we're going to isolate the squared variable and then take the square root. So we see that the square root of x squared gives us x, and squaring the square root gives us x. And finally, we see that the domain of the square root function is going to be all values of x greater than or equal to 0, and the range will be all values of y greater than or equal to y for the parent function. If we transform the function, we'll have to modify the domain and range.